Hey, so good day everyone and welcome again to another science video lesson, and this time we will going to talk about module number 2, and that is locating the earthquake epicenter using seismic waves. All right, in our last video we talked about the lithosphere and anything about the lithosphere, and also we included there the layers of the earth. All right, now in this video we were going to find out if it is possible to locate the epicenter of an earthquake using seismic waves. So with that, let's jump right into it. All right, so this is our topic. So the question here is, can we find the location of the earthquake epicenter using seismic waves? All right, that is the I hope this discussion will be answering that question. And in this particular discussion also, you will learn how to use triangulation in finding the location of the epicenter. All right. So what is an earthquake? All right. So what is an earthquake? An earthquake is a natural disaster. All right. That is a natural event. Okay. And when it starts, or when there is an earthquake, buildings that are not sturdy enough suddenly collapse. Okay, and definitely, when we talk about an earthquake, what is an earthquake? This is the sudden shaking of the Earth's surface. All right, this is the sudden shaking of the Earth's surface, and you don't know the exact and the definite time when the shaking of the Earth's surface will start. All right, so the earthquake will just come. All right, it will just come by. All right, and it will start shaking the ground definitely. Okay, without any warnings or whatever. All right, now as it does, okay, it releases the energy in the Earth's lithosphere that creates this seismic wave, which we will going to discuss later. All right, so these seismic waves are very important in determining the earthquake distance or the epicenter distance and the location of the epicenter respectively. Okay, so again, earthquake is a sudden shaking of the Earth's surface. Okay, in these are the things that you need to be familiar when there's an earthquake. All right, so these are the terms, right, that you can that is associated when there is an earthquake. So first one is fault. All right, first one is fault. Fault is a fracture in the rock that makes up the earth's crust. All right, so the rocks, okay, when they are subjected to deformation during an earthquake, the tendency is the fracture are likely to be formed in these rocks, okay, on the area where an earthquake happens. Okay, now on the same area that you have right here, there's what they call an epicenter. So what do you mean by epicenter? This is the point in the surface above the focus. All right, this is the point at the surface of the earth where the earthquake happens. All right, now underneath it is the focus. All right, the focus is this is where the earthquake starts. Okay, again, the focus is the place where the earthquake starts, and above it, the Earth's surface is called the epicenter. You can call also focus as hypocenter. All right. Now, next one is the plates. All right. There will be no earthquakes without the movement of the plates. The movement of the plates triggers this natural disaster or natural phenomenon, okay, called earthquake. All right, next one. As you recall, plates are giant chunks of lithosphere, and they are divided into several large and small plates respectively. So you encountered that one last time in our last video. All right. Next one is, whenever there's an earthquake, seismic waves are generated. All right? These seismic waves are generated and transmitted all throughout the earth itself. Okay, so this is the anatomy of the earthquake, and these are the terms that you should be familiar of when there is an earthquake. Okay, now what happens during an earthquake? So this is the thing that happens during an earthquake. Now, during the earthquake, the rocks are subjected to elastic stress. And this elastic stress is being stored by the rocks, and that is released suddenly during an earthquake. So it is just like a rubber band. It is just like a rubber band that when you stretch it, when you stretch a rubber band, it stores elastic potential energy. Then when you release it, that elastic potential energy will become a kinetic energy. Okay, it will become a kinetic energy. So similar with the rocks underneath the earth. Okay, it stores elastic stress over time, and when they do, they will release that elastic stress, all right? And the strain energy that is accumulated all throughout this process creates these seismic waves during an earthquake. Okay, so the stress that is stored by the rocks over a long period of time, it can be 100 years, 200, 300 years, or even 500 years, it will be released in one definite moment, and this particular energy creates these seismic waves that travels in all direction throughout the earth. All right, so that is what is happening during an earthquake. Okay, so what is this seismic waves? Since we are talking about seismic wave, what are these seismic waves? Seismic waves are vibrations that travels or that moves through the earth. All right? So it can go inside the earth. All right? So it can go inside the earth, or it can even go on the surface of the earth. All right? So whether it is on the surface or it goes inside the earth, it is called seismic waves. So these are vibrations, okay, that goes inside or travels on the surface of the earth. All right. So let's have each in every let's have the types of seismic waves. Okay. So let's have the body wave. So body waves are types of seismic waves that are that travels inside the earth. Okay, to make it simple, body waves are seismic waves that travels inside the earth in all directions. Okay, it spreads in all directions. And the surface wave, well, from the word itself, surface means these are seismic waves that travels only on the earth's surface. Most of the time, this surface wave causes destruction that is causes destruction on any structure above the Earth's surface. Okay, so there are two types of seismic waves. Namely, we have body waves and we have the surface waves. All right, so let's start first with the body waves. There are two types of body waves. All right, so the one that we have right here is the P waves, or we can call it the pressure wave. All right, now the characteristics of the pressure wave is that it allows the materials, or it vibrates the materials back and forth. Alright, so it vibrates the material back and forth. So as you can see on the picture, it compresses and expands the material, alright, time to time. And as it does, the direction of motion is parallel to the particle motion. Okay? So that is the characteristics of your P waves. P waves are longitudinal wave and also known as compressional wave. So the material, the movement of the material is parallel to the direction of motion. All right? So here we are, right? So aside from that, P waves can travel through solids, all right? And it can travel also in liquids. Okay. So in some cases, P waves also can travel through gas. All right? So those are the materials that P waves can travel through. Right? So that is P waves or pressure wave. The next type of body wave is the shear wave. All right, or the S wave. So S waves are transverse wave. Compared to the P wave, S wave is slower than the P waves. All right? So and the movement of the S wave is, okay, it vibrates the material side to side, and the movement is perpendicular to the direction of motion. All right. So as you can see here, the material is moved up and down in an S wave, and the movement is up and down vertically, and the direction of motion is horizontally. So this is perpendicular to each other. This is perpendicular, and that is the characteristics of an S wave. That is why it is called a transverse wave. Alright, it is a transverse wave. Now, in what material does the S wave do S waves travel to? Alright, let's have first the solid. It can pass through solid. Alright, and also it can pass through liquids. Sorry, it cannot pass through liquid. So that's the limitation of your S wave. And also, if the S wave cannot pass through liquid, so there is a definite, all right, it cannot also pass through gases. All right, it cannot pass also through gases. That's the reason why S wave are only transmitted in solid materials. All right. So now I will leave a question to you. Why is it that in liquids and gases S wave cannot travel? What makes this material doesn't allow S wave to travel onto it? All right. So if you have the answer to that question, you can write it down, or you can type it down in the comment section below. All right. So now let's go now to the surface wave. So surface wave are seismic waves that is transmitted or that travels along the surface of the earth. Now the first type of wave under surface wave is the lob wave. All right. So the lob wave is a type of wave, right? It is a type of wave that runs through the surface of the earth, but the direction of motion and the particle motion is perpendicular to each other. Now, it is similar to the S wave, but it travels on the surface. Alright, so as you can see here, the motion of the particle is horizontally sideways, and the direction of motion is going that way, going this way. So what happens is there is it is perpendicular, all right, to the direction of propagation of the wave. Now, as you can see on this picture, the road over here is subjected to the passing of the lob waves. So what happens here is the road is bent, all right, side to side. Okay, as well as this railroad that you have right here. Okay, so a lob wave passes through this area during an earthquake. So it bends, right? It bends the railroad on this area respectively. All right, so the next type of surface wave is called the Rayleigh wave. All right, so the Rayleigh wave is completely different from the lob waves. It doesn't go sideways. All right, it doesn't go up and down. All right, what it does, the movement of your Rayleigh wave is circular. All right, the movement of your Rayleigh wave is circular, counterclockwise. All right. So this is one of the most destructive wave under the surface wave. So as you can see here, it lifts up the ground and it drops the ground respectively. Okay, imagine you have a water wave on ground. Right? Imagine that you have a water wave. Imagine that you have a wave similar to a water wave that runs on the Earth's surface. That is the Rayleigh wave. Now, to further understand how Rayleigh wave works, let's watch this video that we have right here.
As Rayleigh waves travel in backward rotating circles, they cause the ground to accelerate through a vertical lift.
All right, so as you can see here, you have your vertical lift. So as you can see earlier, you have your vertical lift. So it throws the structure upward. All right, it throws the structure upward. Then after that, it throws the structure, or it pushes the structure horizontally. Okay, in this direction. Next one.
Vertical drop.
All right, so if you put the structure, if you throw the structure upward, then there is a point in time that the Rayleigh wave also has this vertical drop. So it drops the structure. Okay, it drops the structure immediately. Then after that, okay. Now after that, okay, it pushes the structure to the opposite direction. All right, so this is the signature This is the signature motion of your Rayleigh wave that you have right here. Okay, so what happens to the structure above is it will definitely collapse if it is subjected to those four forces that you have right there. Okay, so vertically up, all right, there's a force that goes upward, there's a force goes on the right direction, and there's a force that goes downward, and there's a force that goes on the uh, left direction. Okay, so if your building is not sturdy enough, it will collapse when a Rayleigh wave passes through it. All right, so that is the Rayleigh wave, another type of your surface wave, respectively. Okay, so those are the different kinds of seismic waves. All right, and okay. Now, the device that is used to detect these seismic waves, are called seismograph. All right. The one that you see here is an improvised seismograph. The one that you have right here has a weights, and the weight that you have right here is fixed in a string, and underneath it there is an ink. Okay, there's an ink, all right, at the bottom, and the paper on it, and once the ground shakes, it will it will scribble down the paper, okay, corresponding to the direction, or to the direction of shaking. All right, so that is the seismograph. Now, nowadays, we have now the modern seismograph, and it looks like this. Again, seismographs are devices that used to detect. All right, they are used to detect, not to predict earthquake, ha? Yan. So, it is used to detect seismic waves. Yeah. Now, in a modern seismograph, it looks like this. It scribbles, right? So this is it contains some ink, and the paper runs through it, and this particular needles that you have right here scribbles down, corresponding to the magnitude, all right? To the magnitude of shaking, all right? To the magnitude of the earthquake that is on that particular area. All right, so that is the modern seismograph, and it looks like this. Okay, so it contains a drum roll of paper, and these scribbles, later we will try to read this one, and we will try to understand what is the how can we find the epicenter distance using this data coming from a seismograph reading. All right, so now, this seismograph over here is burrowed underground near a volcano, near a fault line, near a tectonic plate, or sometimes it is burrowed or it is placed underwater, and it is somehow used to detect tsunamis. All right, in some places. Okay, so that is the importance of your seismograph over here. Now, seismograph is a very important tool in on geologists. All right, in some geologists. Okay, this is one of their handy tool. And how many of this seismograph are placed all throughout the planet? All right, so there are a lot. All right, there are a lot of seismograph that are placed in different parts of the planet, and all geologists on the planet are working all hand in hand, are helping each other out in order to prevent the loss of lives during an earthquake. All right, especially the tsunami warnings. All right, the tsunami warnings in some coastal regions that you see here, like the one that we have right here. Right, so there are seismographs on that area, and modern seismographs can transmit data wirelessly. Okay, they can transmit data wirelessly, so that any people that is living in this coastal area can be warned, all right, ahead of time, and can evacuate immediately, all right, before the tsunami comes on that coastal area. All right, so these are the seismographs placed on the entire planet. All right. Now, What are the factors that affects the speed of your seismic waves? What are these factors? All right, so let me have first the two factors. There are four of them. All right, there are four of them, or there are five of them respectively. Let's discuss first these two factors that we have right here. First one is the density and rigidity. All right, so the density of the material affects the velocity of the P and S wave, and also the compactness of the material, or the rigidity. All right, so the idea was that the seismic waves will travel faster, their velocity will be higher at denser materials and rigid materials. For example, a solid materials can transmit seismic wave much faster than a liquid material. All right, so things like that. Okay, and aside from that, seismic waves also are subjected to reflection. All right, so what makes these seismic waves reflect? All right, what makes them reflect? Now, if the seismic waves encounter a material which they can't pass through, like liquid or something like that, okay, what happens here is the waves are being reflected. Now, when they do reflect, it will be picked up by the seismograph on that certain area where they reflect. All right, so that is the effect of the material. All right, that is the effect of the material on the waves traveling on that particular layer. All right, next one. Aside from being reflected, waves are also being refracted. Okay, if reflected means bounce back, refraction means bending. All right, waves are subjected to bending. All right, why do waves bend, or why do seismic waves bend? Now, when they encounter a material with different density, seismic waves are likely to be refracted. Alright? They can pass through that material, but the speed of that particular wave will be slower than usual. Alright, so it will look like this. Okay, let's start first with reflection. Now, when a certain wave, like the one that you have right here, when a certain wave encounters a layer which it cannot pass through, right? It is likely to be reflected or bounce back. Now, when it does, it will be picked up by the seismograph over there. All right? So, we can conclude that this layer doesn't allow this type of wave to pass through this layer. All right? So, next one. Okay, waves are likely to be refracted, especially when they encounter when they encounter a layer in which this layer slows down its movement. All right. So if the layer is permitting high velocity, or is permitting the seismic wave to travel faster, then it goes like this. Now, if it encounters a layer that slows it down, it will look like this one. All right? So, there's a bending. There's a bending of the wave. All right? So, in the process, then that is seismic wave refraction. Okay? Now, the seismic waves when there is an earthquake. Okay? For example, the earthquake happened here and the focus is over here, right? So, when there's an earthquake, seismic waves are generated. Now, just like when you throw a stone in a pond, all right? Just like when you throw a stone in a pond, all right? The water wave will start where the stone landed. Okay? And then the wave will spread outward, coming from the center, it will spread outward in all directions. Alright? The seismic wave is similar to that. Alright? When there is an earthquake, the seismic waves are transmitted in all directions that you have right here. Alright? It is transmitted in all directions. And as you can see, the waves are curved. Alright? So, the waves are curved. Okay, what is the reason behind that one? Because as the waves go deeper down the earth, its velocity is increasing. Alright? Its velocity is increasing. That is why in some point in time, it is curved. Alright, so again, seismic waves are transmitted in all directions, okay, and it travels in a curved path. Okay, so aside from density and rigidity, we have also temperature. Alright, it affects the speed of your seismic waves, okay, respectively. Okay. Okay. Okay, so this particular picture shows you how the seismic waves are being transmitted all throughout the Earth. First thing is the surface wave. Okay, it travels mostly or it travels only on the surface. And the one that you have at the bottom, the blue and then the green one, are the body waves. As you can see, they can pass sometimes or some of them are reflected and some of them are refracted respectively. Okay, so these are the seismic waves. Okay, so as you can see from this diagram, it tells us that as we go deeper, all right, so as we go deeper from crust to inner core, the density of the material increases. All right, the density of the layer increases. So it tells us or it gives us the conclusion that the deeper you go, all right, as you move towards the core, the density increases. Alright, the density of the material over there is increasing. Okay. Now, to sum up, alright, so to sum up everything, so there are four. Let me clarify that one. There are only four factors. So, as we talked about earlier, increasing depth means increasing seismic wave speed. Alright, so increasing depth. Now, the denser the material, the higher the velocity of your seismic wave. Right, next one. In terms of temperature, alright, in terms of temperature, the motion or the seismic wave is likely to decrease. Alright, the speed of your seismic wave will decrease. And upon increasing pressure, the speed of your seismic wave will increase. Now, the question that I want you to answer is, why is it that when we increase the temperature, the speed of your seismic wave decreases? All right. So, what happens, all right, what happens when you increase the temperature? Why is it that the seismic wave velocity decreases? Okay, so if you know the answer, you can write it down in the comment section below this video. All right, so I'll just give you a clue. It has something to do with the movement of the molecules when they are heated. Okay, the movement of molecules when they are heated. Okay, so that is the factors that affects the velocity of your seismic wave. Okay, now we have right here, all right, we have right here a typical seismograph reading. Okay, and how to read this one? Okay, let's start first with the body waves. All right, so the body waves is the seismic waves that can travel inside the earth, right? So there are two types of them. So we have the P wave and S wave. So as I've said earlier that the P waves travel faster than S wave. So if you read the seismograph, you will see that the P waves are arriving earlier than the S wave. Alright? And the S wave follows through. And the large amplitudes of waves that you have right here are called the surface wave. Alright, it contains already the data from Rayleigh waves and lab waves respectively. Okay, so this is the surface wave. Alright. Now, in determining the epicenter distance, alright, we will look forward on this two body waves that we have right here. Alright. Now, I have a question on you guys. So, which do you think? All right, which of this reading is near, all right? Which of this reading is near the epicenter distance? All right? Which of this reading is near the epicenter distance? Okay, you can pause this video, all right, if you want to answer the question. All right? So, think of it first. Which of these readings are near the epicenter? Okay, of an earthquake. Okay, so the answer is letter C. All right, the answer is letter C. Why? It's because, all right, in terms of the amplitude of the P wave, okay, this is much higher than the one you found on B and letter A. So making letter C the one or the seismograph which is near the epicenter. Meanwhile, the A is far away from the epicenter. Alright, so this is far away from the epicenter because the amplitude of your P wave is slightly lower than the one that you have on letter C. All right, letter B is in the mid range. All right, it's not near, it is not so far as well. All right, so that is your that's how you determine the epicenter distance. Okay, the distance to the epicenter using only the seismograph readings that you have right here. All right. Now, on our next part, how do we find the location of the epicenter using seismograph readings and triangulation method? Right. So in this case, I will use a video from that I downloaded from YouTube. All right, to somehow explain or to help me explain this one by one. All right. So the link of the video is below is it is on the description below this video. So try to visit the author of the content of this video and put a subscribe or hit a like on his video. All right, and it will help him a lot. Okay, so let's take a look at that video. Alright, so here in this video, okay, so it will teach us how to analyze seismogram readings. Okay, so in this case, okay. Alright, so in this case, we will try to find out how to locate the epicenter distance using the seismogram reading. So as you can see here, you have your seismogram reading over here, and below it, we have the time. Okay, so below it we have the time. So the time can vary. We have an hour, okay, so and minutes and seconds. Some of the seismogram readings doesn't have hours and only minutes, and some seismogram readings are having seconds only, no minutes. All right. So it depends upon the data or it depends upon the location of the seismogram. Okay, that affects the variation of time on it. All right. So, as we all know that the P waves travel faster than S waves, so we can identify on this seismogram reading that this will be the P wave and this will be the S wave respectively. Okay, so with that, okay, with that, we will put now different parameters in finding the epicenter distance. Number 1, we have the P wave arrival time. Then number 2, we have the S wave arrival time. Number 3, we have the lag time. Then we have the epicenter distance. Right? So we have the epicenter distance, and after getting the epicenter distance, we will get now the P wave travel time. Alright, so how long did the P wave travel from the epicenter to your place? Alright, to the place where the seismogram is located or seismograph is located, and as well as the S wave travel time, and we will find the origin time. Alright, so how far did these two waves travel respectively from epicenter to the seismograph that detects that particular waves. All right. So let's start first with the P wave arrival time. So how do we get the P wave arrival time? Now to get the P wave arrival time, okay, so that is the P wave. So as you can see, the P wave started to rise at this point. All right. So that is the point where you will get the reading from your time below. All right. So do not use the peak. Instead, you use the time it started to arrive. All right, the time it rises up. Okay, so in this case, we have 8:21. All right, so the P wave arrived at 8:21 because that is the time the wave or the reading started to go up. Okay, the P wave started to go up at 8:21. So, respectively, 8:21. Okay, so why is 8:21? Because this is 8:20 and this mark will be 8:21, 2, 3, 4, 25. All right, so that is 8:21. So you put it there on your on our data table, 8:21, 8 hours 21 minutes. Now let's take a okay, we all know that the S wave arrived later than the P wave. All right. So, as you can see, the S wave started to rise over here. Right? It started to rise over here. So, we will use that part or we will use this place to find the time of arrival of your S wave. And we see that it is around 8:30. So, let's see if we are correct. So, that is 8:30. So, at 8:30, the S wave is has arrived. All right? And it was picked up by your seismograph respectively. So at 8:30. Now, let's take a look at the lag time. The lag time is the difference between the S wave arrival time and the P wave arrival time. That's the lag time. All right? That's the gap. Okay, that's the gap of the arrival time between those two waves that you have right there. Now, how to get the lag time? So, from its definition, the difference, which means that you will subtract P wave and S wave respectively. Right? So, it will look like this. Okay, so to get the lag time, okay. So, to get the lag time, you will subtract S wave arrival time with the P wave arrival time, that is 8:21. Alright, and you will get 9 minutes. All right. So put that 9 minutes on our data table. That is the lag time. And lag time is very important in finding the distance to the epicenter. Okay, this is very important. Any mistakes in your lag time will affect the epicenter distance. So, how do we find the epicenter distance? So, the epicenter distance is obtained, all right, using the P wave and S wave travel time curve. Alright, so let me introduce this curve to you. Now, on this curve, it is a graph. Alright, it is a graph between travel time in minutes and epicenter distance in kilometers. The one at the x-axis. Alright, so in the travel time, there is an interval, all right, between minutes that you have right here. And the epicenter distance also has also an interval. Now, epicenter distance is in 1,000 or 1,000 kilometers. So we have here 1,000, 2,000, 3,000, 4,000, 5,000, so on and so forth kilometers. All right. And the interval, all right, the interval between distances, the interval between epicenter distance is by twos. So we have 200, 400, 600, 800, and 1,000 kilometers. So later as we zoom in on that part, we will see the intervals that I'm talking about. Now, there is a line over here. So the topmost line is the S wave and the bottom one is the P wave. So the one that is on the gap over here, the one that is on the gap, this is the wedge. Alright, this is the lag time. Alright, this is the lag time between the arrival of P waves and S wave respectively. Alright, so how to use this travel time graph? Alright, all you need to have here is the lag time. Okay, so all you need to have here is the lag time taken from the data table that we have earlier. And all you need to have also is a piece of paper. Okay, make sure that the scrap paper that you will use has a straight edge. You can use a ruler if you want to. Okay, and you have a straight edge on that and place it on the travel time graph. All right, so place it on the travel time graph and put a mark on it. All right, put a mark on it. So what mark are you going to put? The lag time. All right, so you will going to put here a mark that indicates your lag time. So it looks like this. All right. So starting from 0 to 9, because our lag time is 9 minutes, that is why 0 to 9 only. So that is your lag time. So you will put a mark there. You just draw a line from 9 and 0. All right. So the next one is, okay, you will scan down the wedge using your lag time. You will scan down the wedge and find out where will these 2 points will align. Okay, you will try to find out on the wedge which part of the wedge, what part of the wedge will these 2 lines, the one at the top and the one at the bottom, will align itself. All right. So it is somewhere here. Okay, so it is somewhere here. It is aligned now. Now, after that, okay, using your ruler, you make a line from the bottom down to the bottom or down to the x-axis. Okay, so you will make a line from the bottom of your mark down to the x-axis where the epicenter distance is located. Or there you have it. Okay, so you have now your line. And to determine the epicenter distance, it landed on 7. Alright, it landed on 7. Then the interval was 200, 400, 600, 800, and 1,000. Alright, so it doesn't touch the 8. So it means that it is between 7,000 and 8,000. So in this case, the line landed on 600 mark. Alright, 600, and that will be 7,600 kilometers for the epicenter distance. Now we got the epicenter distance. We can now put it on the data table that you have right here. Now, what is the importance of this epicenter distance? Now, the epicenter distance will tell you or will guide you where the exact location of the epicenter on an earthquake that happens on a certain area. So, it will tell you. Now, okay. So, next one, how to find the P-wave travel time. Now, to find the P-wave travel time, all we need to use is the epicenter distance. This is very crucial. Any mistakes in the epicenter distance will affect the one that you will find on your P-wave travel time. Alright, so let's go back to our travel time curve and find out the P-wave travel time. Alright, so to find the P-wave travel time, you mark the 7,600 kilometer epicenter distance and draw a line vertically upward going to the P-wave. Right, so going to the P-wave vertically upward, then there you have it. And draw a horizontal line from the point where the vertical line touches the P-wave, and draw a horizontal line that goes to the y-axis, and we have the reading of 11 minutes. So the P-wave arrival time is 11, or the P-wave travel time rather, is 11 minutes. So let's put it down on the data table. So that is 11 minutes. Okay, so what does this one means? What does this one means? It tells us that the P-wave travels for around 11 minutes starting from the source of the earthquake. Alright? So the P-wave traveled from the epicenter to the location of the seismograph at around 11 minutes. Alright? So, next one. How do we find the S-wave travel time? So, to find the S-wave travel time, what you did on the P-wave is the same thing as on the S-wave. So, first, you will draw a vertical line coming from the 7,600 kilometer mark. Then, it goes up to the point where the S-wave line is located. Then, as it does, you draw again a line horizontally going to the y-axis, and then you will find there the travel time of the S-wave, around 7,600 kilometers. And that was 20 minutes. Alright, so there is your 20 minutes, and let's put it down on your data table. That is 20 minutes. Now, how do we find the origin time? How do we find the origin time? Now, to find the origin time, you will just subtract P-wave arrival time to P travel time. And you will subtract as well the S-wave arrival time to S-wave travel time. Alright. When you do subtract those two to its travel time, they should have the same answer. Alright, let's have a quick look about that on that one. Okay, you will subtract P wave travel time and P wave arrival time. Alright. When you do, you will get P wave arrival time minus P wave travel time is equal to 8 hours and 10 minutes. Alright, so that is the origin time of P waves. Alright, that's the origin time of P wave, 8:10. Now, this origin time of P wave should be the same, as the S wave. Okay, so let's take a quick look on that one. Right. So subtract S wave arrival time to S wave travel time. Alright. So when you do, it should be the same thing. 8 hours and 10 minutes. Alright, so our origin time is 8 hours and 10 minutes. Right? So that is how you obtain the data coming from the seismograph readings above. Okay, so we have the P wave arrival time at 8:21. We have the S wave arrival time at 8:30. We have the lag time at 9 minutes. Alright? And the epicenter distance that we got from this reading is 7,600 kilometer. How long that the P wave traveled from the epicenter to the place where the seismograph is located? 11 minutes. Also, the S wave traveled for around 20 minutes, and both waves has an origin time of 8 hours and 10 minutes. Alright, so that is how you interpret your seismograph reading. Now, this time, we will now go to the triangulation method. Now, in the triangulation method, what we will going to use is only the epicenter distance. Alright, so we will use only the epicenter distance. Alright, so let's take a good look on that. Okay. Again, don't forget to like this video from our generous author. Alright, so I will put the link of the description or link of this video down to the description below this video that we have. Alright, so this time, how do we find the epicenter using triangulation? Alright, so as I've said earlier, the most important data that we need here is the epicenter distance. So by using the epicenter distance, we will try to find the epicenter. Alright, so generally speaking, we can when there's an earthquake, there is no way that you can find the epicenter, or there's no way locating the epicenter of an earthquake in highly precise manner. Okay? It is impossible to locate the exact location of the epicenter by just using the amount of damage that happened on a certain area. Okay? So you can use that one, but it is not that precise or accurate. Alright? It is not that accurate to use the amount of damage that happened on an area to say that that is the epicenter. Now, how do we find the epicenter in a more accurate means? Okay, so with the use of seismograph readings coming from three stations. Take note of that one, 3 stations. Not 1, not 2, but 3 stations. Alright, so we can use 4. Alright, we can use 4, but 4 is excessive enough for this one. So the minimum is 3. Right. Okay, so we have now your 3 locations that you have right here. Okay, so 1 over here, over there, and down below. Okay, so and also we need the 3 seismograph readings from these 3 stations. Now, without this reading, it is impossible to find the epicenter using the triangulation method. Now, what is important here is this seismograph reading. Now, let's find out where is the epicenter from this earthquake scenario that we have right here. All right. So the first station. All right. So the first station, we determined the epicenter from the first station, and we determined that it is around 700 kilometers. Right? It is around 700 kilometers from the epicenter. So, what are we going to do is we will make a radius. We will draw a line from the center. All right? From that point going to that 700 kilometer. All right? So, in all directions. Okay, there you have it. Okay, and you draw a circle. Okay. Now, if you are using a small map, and a ruler, alright, you might want to scale it down. Alright, you might want to scale it down because 700 kilometers is not or cannot fit in a small map and a ruler. Alright, it cannot fit in a small map and a ruler. So, you need to scale it down into something that will make it small. Alright, that will make it small but the same distance. All right, the same distance that we have right here. For example, we have 1 centimeter is to 100 kilometers, something like that. 5 cm is to 100 kilometers. Okay, things like that. You need to scale down. All right, next one. Let's go now to the second station. Right. So the second station has a reading or has an epicenter distance of 3,000 kilometers. All right. So, the 3,000 kilometers. Again, 3,000 kilometers will not fit on your ruler, so you need to scale it down. The scale that you used here, must be similar to the scale that you will use on number 2, and not only on number 2 but also on number 3. All these three seismic stations must have the same scale that you used on seismic station number 1. Okay, let's draw a line. Let's draw the radius from seismic station number 2, 3,000 kilometers, and draw a circle. Alright, so we have now the 3,000 kilometer radius circle. So, what do we have right here? Now, we got 2 epicenter. Again, 2 epicenter is, it is impossible to have a 2 epicenter. Alright? If there's an earthquake, there should only be 1 epicenter. So, having 2 epicenters here are very, we can say it is vague. Alright? So, we need the third and last seismic station in order to find out the exact location of the epicenter. Which of these 2 epicenter is likely to be the epicenter of the earthquake? Okay, so let's go to number 3. Alright, number 3 found out that the distance from the epicenter distance is 3,500 kilometer. Right? So that is 3,500 kilometers. So, we will go again, a warning. Alright, please be reminded that whatever scale that you use on seismic station number 1 must be the same in all seismic station that you have right here. Alright, so let's draw a radius. Alright, let's draw a line and let's draw a circle. Alright, now, in order to find the exact location of the epicenter, the 3 lines from these 3 circles that you have right here, from number 2, then your number 2, then your number 3, the lines from these 3 circles must overlap each other to a certain point. Alright? And that overlapping of those 3 circles happened here, and that will now be the epicenter distance. Alright? This is now your epicenter not epicenter distance, clarify, epicenter location. Alright? So, that is now the location of your epicenter. Alright? So, just put a star on it. Okay? And there you have it, the epicenter location, using the distance that we got from a seismograph reading that we used earlier. Okay? So that is, the process that you see here is called the triangulation. Alright, so let's go back. Okay. That is the triangulation. So, with that, let's go now to the application of our lesson that we have today. Okay. Alright, now what did we get in studying the seismic wave? Alright, aside from getting the epicenter location, we determined as well that there is something on the core that creates this P wave shadow zone. Alright, there is something on the core with the use of seismic waves. There is something on the core that creates this shadow zone, and it gives us an idea that that part of the core slows down the P waves on that area. Alright? Now, if it is not slowing down, there should be a wave on this shadow zone that you have right here. But as you can see here, there are no waves coming here. Alright? So it means that the core has something in it that slows down this P wave. Now, using the S wave, we determined that the core is liquid. That one part of the core is liquid and one part of the core is solid. So, it tells us that the S wave cannot pass through this area. Instead of passing through, it is reflected outward. It is reflected outward this area. So, meaning to say, it is something that the S wave cannot pass through, and that is, based on what you have learned earlier, that is liquid. Right? So, meaning to say that the core of the Earth is made up of a liquid outer core and a solid inner core, respectively. That forms this S-wave shadow zone that is so big that no S-wave passes through this area, or no S-wave is received by the seismograph on this area that you have right here. Right? So, there you have it. Okay, so there you have it. So, next one. Okay. And aside from this one, we can also use seismic waves. We can also use seismic waves in determining the oil deposits underground. Alright? We can use the seismic waves in determining the oil deposits underground, because S-wave cannot travel to liquid. Oil deposits are in a form of liquid material. Okay, so natural gas and oil deposits are technically material in which the S wave cannot pass through. So the petroleum engineers uses S wave in order to detect, where are these oil deposit and natural gas deposits located underground. Alright, so that's the importance of using the S wave or the seismic waves. So maybe without these seismic waves, we do not have any oil that we will going to use to power our power plants, move our cars, and then so on and then so forth. Alright, so that is the application of studying the S waves or the seismic waves in this particular lesson that we have right here. Alright, so before we end, okay, these are the things that we have learned today. So number one is the earthquake. Earthquake is the sudden shaking of the ground, and earthquake releases the energy and creates these seismic waves respectively. Now, you know already the anatomy of an earthquake. When there's an earthquake, you might likely to find out where is its epicenter, and also its focus, and where is the fault that the earthquake occurs. All right, so these are the things that are part, or these are the terms that are part of an earthquake anatomy. All right, next one, the seismic waves. Seismic waves are waves that travels all throughout the earth. It can be a body wave that travels inside the earth, or it can be a surface wave that travels on the surface of the earth. Now, the body waves has two types. We have P waves, which is faster than its brother, which is the S waves. All right, so P waves are longitudinal wave. S waves are transverse wave. All right, next one. All right. Next one, the surface wave is divided into two. So we have lob waves and the Rayleigh waves. Right? So these are the two kinds of surface wave. Now, the factors that affects the speed of the seismic waves, there are four. We have temperature, we have density, we have depth, and we have pressure. Alright, so those are the four factors that affects the speed of your seismic waves. And finally, in this lesson, you determine the epicenter distance. Right, so you determine the epicenter distance using triangulation and using the seismograph reading. So by now, after this lesson, you now know how to read the seismograph readings. Alright, so you can now be a geologist. Okay. So these are the things that we have learned today. So if you learned all these things today, so let's give it a high five. High five. And that is a great success. Okay. All right. So that ends up our video lesson at this point in time. So I hope you did get a value from this video. So if you get a value from this lesson, so you hit the like button and hit the notification bell button and subscribe button on this video for you to be notified to more videos or science videos like this one that I have right here, for you to be notified in the future. And don't forget to comment. All right, I accept some criticism and comments for this video. All right, so let me know, and it will help me a lot in improving more science video lesson in the future. All right, so give it a thumbs up, guys. It will help me a lot. All right, that ends up the video today, and let's see each other on the next science video lesson. All right, goodbye, guys, and make yourself safe and productive.